In this second example, we have amended the previous problem to include more elements. A pulley is now mounted at the intersection of the bar and cable AC at A, and the second cable, also attached at A, descends to and wraps around a small pulley at D before ascending up, over, and around A to be secured to a spool attached to a motor at E. When the motor runs, the engine block can be raised or lowered. If the engine block rises or falls vertically at constant speed, the equations of static equilibrium still apply because it is a non-accelerating system. In this problem, we want to determine the largest weight of the engine block that can be lifted, given the member failure strengths listed. Although we are ultimately solving for the weight W, we will treat this as a known quantity. Our goal is to find the loads carried by the structural elements as a multiplier on W, because this representation, combined with the failure criteria, will ultimately decide the allowable weight. You may be tempted to substitute one of the given failure strengths in for the load carried by an element, but we don't know which structural element reaches its failure criterion first, and they won't all reach their failure loads at the same time. For now, we'll label the engine block weight as W and treat that as known. We have three structural elements in the problem carrying forces we don't know: cable AC, cable ADE, and bar AB. In keeping with our general guidelines to isolate locations with interacting members, there are two locations of interest: the pulleys at D and at A. In these cases, we will not concern ourselves with the details of the pulley assemblies. Instead, we will draw enveloping surfaces around these pulleys where all of the internal forces between elements of the pulley assembly are interior to the enveloping surface and don't appear in the free body diagram. The only forces that will appear in these cases will be those that are associated with cutting through different structural elements. At D, we cut through the cable ADE at two separate locations, and those are shown here. We'll label both of these TADE. We're also cutting through the hooked member that's carrying the engine, and the force that develops in that member is simply the engine weight W. The force equilibrium equations for the pulley at D are these. In the x direction, we have neither loads nor internal forces. There's nothing in the x direction, and our equilibrium equation is 0 equals 0. In the y direction, we have 2 TADE minus W equals 0, which is going to tell us that the tension that's carried by cable ADE is W over 2. The first equation, while trivial, does have some significance. When motion is not restrained, we get the trivial equation 0 equals 0 as a signature. In the present case, we interpret this as indicating that the engine can experience small amplitude displacements in x, rocking back and forth as it is raised or lowered. As long as these displacements are small, it's not going to have a significant impact on the rest of the problem. Our second equation tells us that the tension in cable ADE is half the engine block's weight. The configuration of cable ADE around pulleys D and A has reduced the load it carries as a multiple of W, but perhaps at the expense of the loads carried by cable AC and bar AB. We need to examine the free body diagram at A to determine those loads. On the basis of the enveloping surface shown above, I've redrawn the pulley with the enveloping surface cutting through 5 different components of the assembly. It cuts through the cable ADE at 3 locations, so we'll add those first. We have a TADE at these 3 locations. We're also cutting through the cable AC, and we're cutting through the bar AB, which I'm going to draw as in compression. Finally, I'm going to annotate this free body diagram with a little bit of information that tells us about the orientation of 2 of these forces in the XY plane. I'll first annotate the inclined tension in ADE with this 3, 4, 5 triangle that tells me something right away about the sines and cosines of that angle. And then the cable AC makes a 20-degree angle with the horizontal that I'll indicate here. On this basis, we can write our force equilibrium equations in X and Y as follows. In the X direction, we have the compression in AB minus the X component of the force carried by cable AC, which is going to be, in this case, minus TAC cosine 20 minus the component of the inclined tension in ADE that goes back towards the motor at E, and the cosine of that angle is 4 over 5, so we have minus TADE 4 over 5 equals 0. In the Y direction, we have the Y component in AC, which is TAC sine 20, minus the component in the inclined segment of ADE in the Y direction. This is minus TADE times 3/5. And then we have the 2 segments in ADE which are pointing straight down, so minus 2 TADE equals 0. Now, since we know that TADE is W over 2, we can solve immediately for the tension in AC in terms of W by rearranging the second equation as 1 over sine 20 degrees times the numerical value that precedes the 2 TADE components when they're added together. So we have a 2, which is 10 over 5, plus a 3 over 5 is 13 over 5, times TADE, but that's also equal to 1/2 W. And that number turns out to be 3.8 W. Then from the first equation, we can take this expression for TAC, substitute that back, use TADE equals W over 2, and we get for the compression in AB that this is equal to 3.8 W times the cosine of 20 degrees plus 1/2 W times 4/5. And that number turns out to be equal to 3.97 W. In summary, we have TADE equals 0.5 W, we have TAC is 3.8 W, and we have CAB equals 3.97 W. The fact that these multipliers are all positive tells us that the directions of the forces sketched in the free body diagrams are correct. In particular, member AB is in fact in compression. To find the maximum allowable weight, we set each of these members equal to its limit load and solve for the corresponding weight. The maximum allowable weight, then, is the minimum of this set. For ADE, 600 pounds is the allowable weight. And that gives us a limiting weight, we'll call it W1, that's equal to 1,200 pounds. For AC, the limiting tension is 3,000 pounds. We'll set that equal to 3.8 W2. And that gives us a second limit on weight, which is equal to 789 pounds. And finally, for AB, which is in compression, we have a 2,000 pound load. And we'll just make a note here that this is in compression, so we're using that number. 2,000 pound load is equal to 3.97 W. We'll call it W3. That gives us a value for the weight that's equal to 504 pounds. The fact that these numbers are all different tells us that each component reaches its limit load at a different weight. The maximum value of weight we can tolerate is the minimum of this set. The minimum of W1, W2, and W3, and that is equal to 504 pounds. In this case, bar AB is the most vulnerable member of the assembly and determines the limit load.